The next part of section 5.1 is about linear independence of functions. So we've heard this word before. Let's just look at this equation for a second and think about this. So we've seen this equation, and can you always find C1 and C2 so this thing works? And the answer is yeah. Like if C1 and C2 are both 0, then this thing works. All right, for no matter what the functions are. But what if you could find other C1s and C2s that weren't 0 that made the linear combination of y1 and y2 equals 0? What would we call them? Well, we would call them dependent. So let's read this definition. Two functions y1 and y2 are linearly dependent if there exists non-zero constants c1 and c2 that you can add them up to get 0, like this equation. The functions are linearly independent if there does not exist such constants. Okay? This can be extended to n functions and n constants as well. So if you can find non-zero constants where you can add up all the functions times the constants and get 0, then they are dependent. So let's determine if some functions are linearly independent or not. And we're just going to kind of wave our hands a little bit here. This first one, about x and 2x. Can you think of something you can multiply with x and then something you can multiply with 2x that will give you 0? Yeah, sure. How about 2 and -1, in which case you get 2x minus 2x, which gives you 0. These are dependent. And let's think about what mattered here. Did the 2 matter? Like if I had a 3, would that make a difference? And the answer is no. You would just change these numbers here and they would still be dependent. What made this important was that they were like terms, right? And so because they were like terms, I could find constants to make them add to 0. Now, what about x squared and x cubed? Can you find C1 and C2 that give you 0 on this one? And the answer is no, right? You can't do that. X squared and x cubed are not like terms, and so there's nothing you can do with this, right? Now, of course, it's true when x equals 0, but it's got to be true for all x's, okay, not just a single x. All right, what about x to the m and x to the n, where m and n are different? So let's just extend that, and the answer is c1 x to the m plus c2 x to the n. This does not equal 0, provided m and n are different, right? So these are independent. I said no, but I meant independent. Okay. Now, these are independent also. I'm just gonna sneak down here and give this corollary before I continue with parts C and D, because I think it's really useful. Two functions are linearly independent if their ratio is constant, i.e. y1 and y2 are linearly independent. Linear is a variable, right? Okay, so when I want to show that two functions are linearly independent, okay, all I have to do is just take these two things here, take x to the m and divide it by x to the n, and you get x to the m minus n. Now, is this constant or is it variable? And you'd say, well, I mean, it could be constant if m is equal to n, and then you look back up here and you say, okay, well, m isn't equal to n, so this is non-constant, so they're independent. And the same thing goes for e to the mx and e to the nx. If you take e to the mx and divide by e to the nx, you get e to the m minus nx, which of course would be equal to 1, provided that m is equal to n, but they're not, so these are independent. And going back to our example over here, if you take 2x and divide by x, you get 2, which is constant, which is dependent, right? This only works when there are two functions. This does not work when there are more functions. Okay, one last thing here. Let's extend this. And this does go back to something we talked about in a previous section. So what about this set here? E to the x, sine x, 0, and 1. Are these independent or dependent? Well, what if I take 0 e to the x plus 0 sine x plus 5 zeros plus 0 ones? Again, who are the coefficients here? That's a coefficient, that's a coefficient, that's a coefficient, that's a coefficient. The rest of them are the functions. And of course, what you get is indeed 0. So any set that includes the 0 vector is automatically dependent. Now, without that, the other three of them are in fact independent, but we don't really know why yet. We'll get back to why later. Now, I want to give us just kind of a warning about this corollary here. So this only works when there are two functions and two functions alone. Okay, if you have more functions, we need more machinery, because just because you have things that are sort of pairwise independent does not mean the set in total is independent. And I have an example here. If you take 1, 0 and 0, 1, those are independent. If you take 1, 0 and 1, 1, those are independent. And if you take 0, 1 and 1, 1, those are independent. But if I then consider the set of all three of them, if you add this plus this, you get this. And so they're dependent, right? So just because you have pairwise independence, meaning the independence of each of the pairs of the three things, does not give you linear independence of an entire set, okay? Just think about that, and that's going to be important when we move on, okay? Next. Here we go. A basis for the solution set of an ordinary differential equation is a collection of linearly independent functions in which the general solution to the differential equation is the span of those functions. All right. Okay. Now we've sort of come full circle here, and we've used all the words that we learned back in chapter 4 about basis, independent, and span. Okay. So, for example, to kind of back up here, if I had let's go at this one here. So these two things were independent here. If I can think of a differential equation in which these two things were both solutions and they were linearly independent, and then this would be the span of all of those solutions, and that would be the that would mean that these two things were a basis for the solution set of that particular ordinary differential equation. All right. Hopefully that made sense. Let me go back and say this next theorem here, because this theorem is really kind of at the heart of what's going on here. And our book doesn't quite say it this way, nor does it prove it. So let me give you let me read it, and then I'll tell you what we've done already. So the theorem says, the solutions of a homogeneous linear ODE of order n form an n-dimensional vector space. All right. What is new and what is easy and what is not easy? So here is the part. The fact that they form a vector space is easy, okay? The property of superposition really gets that for us, okay? When you add solutions, you get a solution. When you multiply the solutions by constants, you get a solution. So the fact that it's a vector space is fairly easy, and in fact, we proved it, okay? So we proved it, well, for degree 2, for order 2, we proved it. But it's not much harder to extend that to something bigger. The hard part of this is the n-dimensional. So that is the hard part. So n-dimensional for order n. Our book doesn't explicitly say that. But what that means is if I have a second order differential equation, then what I'm looking for is two vectors, right? Because what it means is that my basis will contain two things, because that's what dimension means, right? The dimension is the size of the basis, okay? Now, in practice, this is going to be very simple. I'm not going to prove this. We're just going to take this as fact, okay? So, for example, in this example 167 here, it is a second order differential equation. So how many solutions am I looking for? I am looking for 2. If I want to show that they're a basis, all I have to do is show that these two things are independent and that they are both solutions. And that's it, okay? I'm going to get the span for free because of the 2 out of 3 theorem, right? If I show they're both solutions and I show they're independent, well, two functions in a dimension 2 space that are independent will by default span. Okay, so that's all that I have to do. That makes sense? So let's try this one. So show that y1 equals e to the 2x and y2 equals x e to the 2x form a basis of the solution space of this thing here. Sometimes it's called a fundamental set, just in case you see that word too. So what do I have to do to show that these two functions form a basis? Well, I just got to show that they both work. So I need y1 prime, that's 2e to the 2x. And I need y1 double prime, that's 4e to the 2x. So let's just plug all that in. 4e to the 2x minus 4 times 2e to the 2x plus 4 times e to the 2x. And what do I get? 4 plus 4 is 8 minus 8 is 0, so that one works. Then y2 prime is, okay, I got a product rule, derivative of the first times the second plus the first times the derivative of the second. Then y2 double prime is 2e to the 2x plus 2e to the 2x plus 2x e to the 2x times another 2 gives me 4. Let's clean that up. 4e to the 2x plus 4x e to the 2x. Hopefully I didn't do that too fast here. So here's my first derivative. Here's my second derivative. Let's plug all that in. So I have 4e to the 2x plus 4x e to the 2x minus 4 times e to the 2x plus 2x e to the 2x plus 4 times the original, which was x e to the 2x. Okay. So let's see. I have 4e to the 2x minus 4e to the 2x. Those cancel. And I have 4x e to the 2x minus 8x e to the 2x plus 4x e to the 2x. Those all cancel and I get 0. Good. Okay, so they're both solutions, right? Now I need to show that they're independent. So to show that they're independent, I just take y2 over y1, which is x e to the 2x, divided by e to the 2x, and I get x, which is not constant, which implies that y1 and y2 are independent. So we are done. So that means that y1 and y2 form a basis. Of solutions. And actually, I can say that the general solution is going to be y equals a times y1 plus b times y2. So this is going to be the general solution because that forms a basis, and so the linear combination is the span, right? Good.